Hello and welcome to practice number 5 of Science Olympiad Circuit Lab. This will focus on magnets, voltage dividers, and current dividers. My name is Mr. Burleson. So we're just going to go over our lesson of the day as we often do. So what causes magnetism? Magnetism comes from basically two types of sources. One is from electric current, in other words, moving charges. Now this could be electromagnetic movements. Basically, it's caused by the intrinsic property of spin of the electrons. Okay, it normally cancels out, but sometimes, either because owing to an external magnetic field, or spontaneously, or because of the way things are set up, all the magnetic moments can be lined up, which means that you get not all these magnetic moments that cancel each other out, but they're all in a straight line. You also can get it from nuclear magnetic moments, and these are thousands of times smaller than the electron's magnetic moments, so pretty much they're going to be negligible for anything that we're going to be talking about today. So permanent magnets. About 2,500 years ago, it was discovered that lodestone or magnetite was attracted to iron, okay? And it would orient itself north to south, so they could create the very first magnetic compasses, okay? And then in 1269, they found that they could make steel magnetic by rubbing it against a pole of the lodestone. So in other words, it was a way to create additional magnets, okay? All magnets have two poles of opposite effect, north and south, okay? So remember how we talked about electrical charges being positive and negative? We're going to talk about magnetic having north and south poles, okay? And just like electrical charge, opposites attract and the same repulse. So two north poles will push against each other, a north and south pole will be attracted to each other, and two south poles will push against each other. Now, one of the cooler parts about a magnet is that if you break a magnet into two, it turns into two magnets, each with its own north and south pole. So you look in the upper right hand corner here, you had a larger magnet and we broke it in half, and then instead of having a north and south pole, we now have two north and two south poles, okay? And when you look at the magnetic field lines, okay, you will notice that we generally draw them out of the North Pole and around in a loop back to the South Pole. Actually, the loop is continued throughout the material, so the magnetic field lines actually go back through the material. So whereas electric fields, we talk about them radiating from a positive charge and into a negative charge, here it's a loop. So one of the main things we'll ask you to do is we're going to ask you to draw these magnetic lines. So if I draw, where I had broken apart that north and south, or those two magnets, you'll notice that the south pole is now attracted to the north pole. So we're going to have attraction, and it's going to be very well confined, okay? Because remember, the north will loop around to the south, okay? And so the north loops around to the south, and the north here goes straight to the south because, again, it wants to try to complete that loop. And so there's an attraction, okay? Now, let's say we put the two north poles next to each other. Well, they loop back, but you'll notice that I can't draw the lines from north to north, and so that's how you get repulsion. Now, magnetic or ferromagnetic materials are readily magnetized, okay? In other words, those atoms easily orient their electron spins to conform to the external magnetic force. The number one ferromagnetic material is iron, and you should guess that because ferro means iron, okay? And generally speaking, most other materials that we talk about that are magnetic generally have iron in them. Now, paramagnetic materials are slightly magnetic, okay? So they're just very, very low magnetism. And diamagnetic materials are materials which tend to exclude magnetic fields and actually have a slight repulsion to a magnet. Okay, and so these are the things that your refrigerator magnets will not stick to. Okay, and you'll notice that when we look at the repulsion, though, it is orders of magnitude different compared to ferromagnetic materials. If I go back here and I try to put it against iron or iron oxide or nickel iron oxide here, so this is very similar to steel, and then you'll notice that it sticks really, really well. Okay, diamagnetic materials. Okay, now you'll notice that these are really, really, really low susceptibilities, but they're slightly negative. Okay, so you're talking 10 to the minus 5, but only negative. Okay, so the difference, you and I wouldn't be able to notice the difference between diamagnetic and paramagnetic materials because it's so close to zero. But here you've got superconductor, bismuth, mercury, silver, diamond, lead, carbon, copper, water. And this is why you can put a magnet up against copper, and it's not going to and it's not going to be attracted. It's actually going to be slightly repulsed, but it's such a low repulsion you wouldn't even be able to notice it. So, how does a magnetic compass work? A compass is a navigational instrument that measures the directions, that uses the Earth's magnetic field, okay, to point towards the magnetic North Pole. Okay, so now one of the key things to always remember is the magnetic North Pole is not quite at the geographical North Pole, and it moves. Okay, now the other thing is that Earth's magnetic North Pole is actually a South Pole when we talk about the magnetic field. Because remember, the compass, the part of the compass that points towards it that we call north and we define as being the north side, is actually attracted to the magnetic South Pole. So there's the physical North Pole, which is in the Arctic, which is usually somewhere in Canada. Okay. And so generally speaking, when we break out our compass, that's what it's pointing to. Okay. However, that point where that it's pointing to is actually a magnetic South Pole. Okay. And just keep in mind, compasses generally become useless the closer you get to the poles. And the reason why is you've got so much magnetism pouring out of the poles, of the magnetic poles of the Earth. Your readings don't work anymore. Okay. Now, the Chinese actually during the Han Dynasty invented magnetic compasses, and then Europe invented a dry compass around 1300 using the same concept. Now, a very common thing here is that you'll notice that we drew a picture here of the loops. Okay, and you may be asked to draw the loops, and so this is a common thing. You'll also might be asked to draw the arrows on the loops, and remember the arrows, it comes out of the north, goes around, and to the south. Now, when they say draw your compasses, they usually mean they're going to draw, like in this case, a diamond, and one side's the north and one side's the south. The north side of the compass is always, always, always red. Just like when you have a real compass, the north side will always be painted red, and that's how you can tell them apart. And what you'll notice here is that the north side is always going to follow the magnetic line. So if I put the compass right next to the compass, it's actually pointing down, and now it's going to point straight towards there. So it's going to follow the magnetic field lines. So you'll notice when I'm moving this compass around this magnet, it follows the field lines. And this is a very common thing. They'll tell you to draw a diagram like this where you have to draw the direction and label which one's the north. And you'll notice they did that here. They labeled this north and this north and this north, etc. So let's talk about Earth's magnetic field. Okay, so if you look at the magnetic field lines, okay, of the Earth. Okay, this is what the magnetic poles look like. So you'll notice it's still, they're these big loops, and there's a lot of them. Okay, you notice that they come out of the north magnetic pole, which is in Antarctica, which is, south of New Zealand, south of South America, south of Australia, south of everything. Okay, but that's the north magnetic pole, and so the arrows come out around and they go down into the south magnetic pole, and the south magnetic pole is usually up here around Canada. But that's not where the spin axis is. The spin axis is actually in the Arctic Ocean, or excuse me, the Arctic Sea. And so that is where the geographic magnetic pole is. Now, keep in mind there are many different shapes for magnets. If I want to do a magnetic needle, quite often it's got a little bit of a bulk here, so I can put it on a spindle so it can spin around easily. I might have a magnetic ring, also sometimes referred to as a toroid. I could have a bar magnet, which we've seen. Here's a standard little refrigerator magnet, which was basically made out of a magnet that was sliced. And the horseshoe shape is very, very common for a magnet. Some magnets are really nice because they'll mark which one's north and which one's south. That always helps. Okay. Some magnets do it by color, so I know this is the north side and this is the south side. Now, what's the north and south side on these other magnets? I don't know. But if I have a known magnet, if whatever's attracted to this red part here is going to obviously be the south side. Whatever is repulsed by this side is obviously going to be the north side. And so that's how you can figure out the north and south side of the different types of magnets. Okay? And so these are very, very common shapes of magnets. Horseshoe magnets are really neat from the standpoint that you have both a north and a south side. And so you actually have both poles here. So you have a very strong magnetic field here and right in front. And what that does is that it actually sort of improves my ability to grab iron or something. And so this is actually a much stronger magnet than if I just tried to use just one side of a magnet. Ones like this that are very flat actually work very well for attaching things like refrigerator magnets. Well, let's switch gears and let's talk about what is a voltage divider. And so a voltage divider is basically a series circuit that breaks apart the voltage. Remember, the voltage is going to be split among all the resistors, but the current is the same. Okay? So, if I look in this case where V is my source voltage, okay, and remember how we figured out series equivalent resistance is series equivalence is the summation of all the resistors, so it'd be, in this case, it'd be R1 plus R2 plus R3. So the big current going around is I is equal to V source divided by R total using Ohm's law. And then the individual voltages here, V, the voltage of R1 is going to be equal to IR1. V of R2, the voltage across here, is equal to IR2, and the voltage across here is equal to V, or is equal to I times R3. Okay? If we combine those two equations to solve for the voltage as a function of this source voltage and the resistances, we don't even need the current. I can say that each of these voltages is equal to the overall source current times the amount of resistance that I'm looking at, so in this case R1, divided by R total. Okay? And so what that means is the bigger the resistor, the more the voltage, because they've all got the same current, and that sort of makes sense with V equals IR. And so if this is 10 ohms and these are both, let's say, 20 ohms, this is going to have half the voltage of these two. And since these two have the same resistance, they're going to have exactly the same voltage. Now, let's say all three of them had the same resistance. Well, then it's real simple because I know if this is like 9 volts, I hooked up to a 9-volt battery. Guess what? I got 3 volts here, 3 volts here, 3 volts here because it's going to be exactly the same. So it allows you to make very quick calculations, and it also allows you to double check your work, because if you've got a bigger resistor and it's got less voltage than one that's a smaller resistor and it somehow has more voltage, you know you probably made a mistake somewhere. Well, if I have a voltage divider, you know I'm going to come up with a current divider. Now in a current divider, the voltage is the same across all of these resistors, but the current is not. So we remember that to solve for the R equivalent, it's 1 over R equivalent is equal to 1 over R plus 1 over R2 plus 1 over R3. R total is always going to be less than the smallest single resistance. So now I can again solve for the total current, okay? And then I notice that I of R1 is equal to V divided by R1. I of R2 is equal to V divided by R2, and I of R3 is equal to V divided by R3. Okay, so you can already sort of see how this one's going to go, is that if I combine those two equations, I can figure out the current going through R1, R2, or R3 by taking the total current and then multiplying it by the R equivalent, because remember it's going to be, that's smaller than any of the other numbers, divided by R1. Okay, and R2 is the same sort of thing. I would do this and divide by R2, and this one I would divide by R3. The key thing to keep in mind here is that when you look at these, whichever one is the bigger resistor is going to have the least current. Whichever one's got the smallest resistance is going to have the most current. Okay, and that makes sense. I is equal to V divided by R. So therefore, if all three of these, let's say I've got 9 amps coming in here, and this is 10 ohms, 10 ohms, 10 ohms, they're each going to have 3 amps. Okay, and if this is 10 ohms and these two are 20 ohms, and let's say I got 5 amps coming in here, or excuse me, let's say I've got 4 amps coming in here. Okay, well then I know that these two, okay, are going to have half the current of that. Okay, and so what that tells me is that, you know, this one here is going to end up with 2 amps, and these are both going to be 1 amp. Okay, so let's do the in practice quiz. What are the magnetic materials? Give 2 examples. You can go back and look at that. What are the paramagnetic materials? Give 2 examples. And what are the diamagnetic materials? Give 2 examples. And then for here, I want you to draw the magnetic lines showing attraction or repulsion. So in this case, I would do a loop around here, around back. So it comes out, and the arrows would be coming out of the North Pole going to the South Pole. In this particular case, I would draw lines from the north to the south here. Okay, so I got the loop here. Okay, and so there would be arrows going this way. I would have an arrow, I would go from the north to the south here, and I have arrows going this way. Okay, and I'd have arrows going from here to here. And these two would be really, really attracted to each other. Now here, I've got the same arrows going from north to south, and same thing here from north to south, from north to south. But my norths are going to repulse, and my souths are going to be repulsed, because this is going to be a very strong repulsion here. Here, I'm going to have north to south, and so there's going to be arrows here. And then what's going to end up happening is that there is going to be an attraction, and it's going to create this magnet in this ferromagnetic material is going to create turn this iron into a magnet. And so it's going to create a north pole here and a south pole here. And so I'm going to have arrows going from here to here, here to here, here to here, and they're all going to be attracting. I'm also going to have a little bit going around here from north to south. It won't be as strong as this magnet, but it will be very magnetic. Same thing here. North, south, I do my loop around the top here from north to south. The arrow's coming out of the north, going around to the south. but I'm going to induce a south pole here and induce a north pole here, and I'm going to have arrows coming from here down, and I'm going to have arrows coming from here up, and I'm going to have arrows coming from here around back to the south pole, to the induced pole. Okay, another in practice quiz. We have a series circuit, which is a voltage divider. We have 100 volts, okay, and R1 is equal to 100, R2 is equal to 220, R3 is equal to 680, okay. Now, what you'll notice here is that if I added all of those up together, okay, it's going to equal about 1,000 kiloohms. Okay, so that's my R equivalent. Okay, and so if I know that I've got 100 volts, okay, I can multiply that times 100 divided by 1,000. So a tenth of that, so 10 volts would be across R1. Okay, then basically this is going to be there's going to be 22 volts across R2 and 68 volts across R3. And does that make sense? Yes, the largest resistor has the most voltage and the smallest resistor has the least. Now, let's look at this other one, okay? Again, same sort of thing. I'm adding a 1 kilo ohm resistor, an 8.2 kilo ohm resistor, and a 3.3 kilo ohm resistor. And again, I add up all these resistors, so that ends up being 0.5, and that ends up being 12. So it's 12.5. So it's about 2 amps going around. Okay, and so what's going to end up happening here is I take 25 times 1 divided by 25. Okay, and that's going to end up being 1 volt across here. Okay, and then if you look at these other two, I'm expecting to have a lot more voltage across R2 than I am across R3, because again, it's the higher resistance, and since the 25s cancel, okay, and the kilo ohms and cancel, what's going to end up happening is that it's going to end up being 8.2 volts here and 3.3 volts there. Okay, now here we have a current source, and it's 10 amps. So I got 10 amps coming in here, and I got 680 ohms, 330 ohms, and 220 ohms all in parallel. Okay, now again, what you want to do is at first you want to figure out what's the total resistance, okay, and then once you figure out the total resistance, okay, then you can figure out the current going through each resistor. And you'll notice in this particular case, I know that the total resistance will be less than 220 ohms. Okay, so whatever we come up with, it will be less than 220 ohms. And so I'm going to actually let everyone do this one on their own and see if you can do it. And remember, I would fully expect that the least current would go through R1, the medium amount of current would go through R2, and it'd be a little less, it'd be a little more than double what goes through R1, and the greatest amount of current would go through R3. And if we look at this particular case, it's very similar, but I'm going to go ahead and tell you this one's sort of even simpler because you'll notice they're multiples of each other. So if I've got 2.2 kilo ohms, 4.4, and 4.4. Well, if I combine the 4.4 and the 4.4 over here, that's 2.2 kilo ohms in parallel with 2.2 kilo ohms. So I know my R equivalent is going to be 1.1 kilo ohms. Okay? Always look for easy places like this where you can combine things. Okay? Now, I know that these two, since they're twice the resistance, are going to have half the current going through them as this one. So this one's going to have like 2 milliamps going through them, whereas each one of these is only going to have 1 milliamp going through them. Now, here's some practicals you can do at home. Using a compass, figure out the north and south poles of each magnet. Now, this is something you have to be sort of careful with, because if you store your compass near magnets, you could demagnetize your compass, or you could reverse the magnetization of your compass. You could mess it up. So when you do this, make sure you keep your magnets and your compasses apart from each other. Then do a couple of practice cases where you draw the magnetic lines of the Earth on the piece of paper, draw the magnetic lines of different types of magnets. Measure the voltage across the series circuit and total across each resistor. Then measure the voltage across the parallel circuit and measure across each resistor. Remember, we're going to always measure the voltage, and then we'll use the resistance to then determine the current. We're never going to measure the current directly. Okay, so what I'd like you to think about is what happens when a permanent magnet is put under high heat. Why does that occur? What can happen if you drop a permanent magnet, it hits the floor, you hit it with a hammer? Why? By the way, this is one of the more common ways to magnetize something or demagnetize something. What would happen if you put a refrigerator magnet on a completely aluminum refrigerator? What would happen on a stainless steel refrigerator? Start going to level 3 combination, level 4 combination, level 5 combination. You're going to find that, level 5 combination is a lot harder than level 3. And I'd like you to use the voltage divider and current divider formulas to solve the homework problems. Some of them are going to be real easy to do when you do that. Again, we're always looking for the easy way to solve things. Well, that concludes today's lesson. I hope it was helpful.